Hello, my name is Hasan, and I'm going to describe a project that we've been working on to develop a new DSL called Stellar for sparse accelerator design. So over the past year, we've been building a DSL which can be used to express, explore, and automatically generate sparse accelerators. Our work tries to build upon earlier work on the automated development of dense accelerators, but also to extend such frameworks into sparse domains. So firstly, why is a tool like this new DSL even needed, right? What's wrong with our current methods of designing sparse accelerators? So one big issue is that the full design space of sparse accelerators is just very, very wide. There are lots of very diverse sparse accelerator architectures, and they tend to come with very different trade-offs for data reuse, hardware complexity, memory access patterns, or even just the ratio of functional units to the peripheral circuitry that's shuffling data around. But because these accelerators are so diverse, it's hard to understand exactly why they have such different trade-offs, right? It can be hard to find accelerators which change only a single design component from another accelerator so that they can be fairly compared. And that motivates us to enumerate this sparse accelerator design space so that we can have a better intuition over how exactly different accelerators differ, as well as to make it faster for us to explore this full design space. So fortunately, there's already been lots of work in the past on taxonomies and design space enumerations for dense accelerator designs. So we don't have to start completely from scratch. It should be possible to build upon these taxonomies, but to extend them with new axes for sparse designs. So a lot of dense accelerator taxonomies are based around a concept known as space-time transformations. Space-time transforms are a pretty old idea, decades old, in fact, but they've also been very useful for papers published in more recent years. So a space-time transform is basically a function which maps each iteration in an abstract tensor computation onto a physical location in a time within a spatial array. So in theory, this function could be arbitrary, but in practice, people oftentimes restrict themselves to affine linear transformations just because they're a lot easier to reason about while still covering quite a broad design space. And just by changing the exact numbers in the linear space-time transform, we can construct output stationary accelerators or different types of input stationary accelerators or others which aren't shown here. So space-time transforms have mostly been used in the past to describe dense accelerator designs, but we could also try to extend them to describe sparse accelerators as well. So for example, let's consider the output stationary data flow that we showed on the previous slide. So there is in fact a sparse data flow, right, which is analogous to the dense output stationary data flow. So we commonly call this the inner product data flow for sparse matrix multiplications. It's not used all that often, but it's a pretty well-known way of performing sparse mathematics. However, in the sparse case, inner product data flows will have much less data reuse throughout the spatial array, which means that the direct PE-to-P connections are usually replaced with direct I/O connections instead. Similarly, for input stationary data flows, there is an analogous sparse mathmal data flow, which is usually called the outer product data flow in sparse accelerator research. Unlike the inner product accelerator, this one preserves reuse of one of the B matrices, which means that some of the PE-to-PE connections can be preserved. It also removes the need to match the keys of the, or indices of the input outrands, which is one reason why it's sometimes favored. However, it often requires very significant circuitry to merge and sort the outputs, which can be highly scattered. And finally, we can also consider the alternative input stationary data flow I described earlier. So in the dense case, there's not really much point in using this data flow over the other input stationary one. It achieves basically the same reuse and the same hardware complexity. But in the case of sparse accelerators, this data flow is sometimes called the Gustafsson data flow, right? And was exploited by two relatively recent sparse accelerator papers to get better efficiency than the outer product data flow, at least in some specific use cases. So Gustafsson sacrifices the reuse of one of the input matrices, but in return it produces much less scattered outputs, which makes it a lot easier to merge and sort the output results. So output mergers can sometimes be more expensive even than the mathmal units themselves, which means that simplifying them can greatly improve efficiency. However, it's not obvious, right, how to compare accelerators using Gustafsson and accelerators using outer product, because they don't differ in only their data flows when you read prior papers. They also differ in the exact sparse data structures that they use. Accelerators that use the outer product data flow, right, like outer space and SPARCH use sparse data formats called CSC and CSR for the inputs, while accelerators which use Gustafsson, such as Gamma and MapRaptor, use only CSR for all inputs. So this motivates the question, right, like why exactly is it easier to merge outputs with accelerators that use Gustafsson, for example? Is it the data flow itself, or the sparsity formats, or the interplay between the two? So if you just read the papers, it's not immediately obvious how to separate the impacts of all these different design choices. And this motivates us to separate the different design choices that go into making a sparse accelerator, so that we can more easily evaluate each one in isolation and also in context with other choices. So we propose 4 different axes along which to evaluate sparse accelerator designs, which we believe can be meaningfully separated and also allow us to cover a wide design space of existing and future accelerators. So one axis is the functional behavior of the accelerator itself, defined by its input and its expected outputs. Another is the data flow, which is the exact mapping of operations to different points in space and time on a physical spatial array. Another is the sparse and or dense data formats, right, which may be structured or unstructured. And the last axis we propose is the exact load balancing technique, which is oftentimes very simple, but for some accelerators can be very, very sophisticated. So the load balancing technique can affect both the complexity of the network on chip and also the sensitivity of the accelerator's performance to different sparsity distributions. So, the question is, can we extend dense accelerator taxonomies to cover these new design space axes? Can we find a way to describe these axes in a way that's simple and intuitive for people, but also easy for automated algorithms to explore? So Stellar, this new DSL we're building, is our attempt to do so. So our goals with this DSL are to make it easier for architects to separate the concerns that go into building an accelerator and to enable them to optimize each of these concerns in isolation, but also in relation to each other. And after the user specifies these concerns within the DSL itself, our compiler will generate Verilog descriptions of the accelerator and programming interfaces for it. And now we'll go through each one of these separate design concerns, and we'll discuss how our DSL allows them to be specified and how it can extract useful information out of those specifications. So we'll start with how we express the functional behavior of the accelerator. So firstly, our users can express the functional behavior of an accelerator separately from its data flow or its data formats. Right? The DSL uses a halide-like assignment-free notation, which has been used in some prior work for automated accelerator generation. Users describe the exact computations that happen at different index points in abstract iteration space, but without placing a lot of restrictions on exactly when these operations occur. So on the right, we can see a relatively simple example of a matrix multiplication in the DSL. We also support more complicated data-dependent and indirect accesses, but in the interest of time, I've left those slides out, but I'm happy to discuss them if anybody's interested. After specifying the functionality of the accelerator, we can also express the exact data flow that the accelerator supports. So I won't say much here because we've already kind of covered this in the previous slides. And this is pretty similar to prior work for dense accelerator data flows. But essentially, we express data flows as linear transformations from some abstract iteration space to physical coordinates and time steps on a spatial array. We also use the data flow to construct ideal dense accelerators which have the highest amount of data reuse possible and which share as much data as possible directly between PEs. However, as we discussed earlier, sparse accelerators often have much less data reuse, and some of those PE to PE connections need to be broken because they will no longer carry useful data between PEs. Instead, some of those connections are replaced by direct I/O connections to the outer memory system based on the sparsity format. But the exact PE to PE connections that are broken depend on the exact sparse data structures that the user wants the accelerator to support. So, for example, PE to PE connections that must be broken with CSR data might be able to be maintained with data in the CSC sparse format. And that means that we need to be able to represent the exact sparse data structures that will be supported as well. So stellar represents sparse data structures in terms of which iterators might be skipped and under which conditions they are skipped. For example, iterations might be skipped because a single value in one of the input matrices is 0, or because a whole row or block in an input matrix is 0, or based on the iterator values themselves, such as when using diagonal sparsity. And the important thing to note is that the sparse data structures can be specified independently from the data flow and the functional description. And in fact, we can extract useful information out of the sparse data structure itself, even without knowing the data flow or anything else. So for example, I mentioned earlier that gamma is a sparse maximal accelerator, which is named after the Gustafsson data flow, and which was able to greatly reduce the size of their output mergers compared to something like outer space. However, there are quite a few differences between the gamma and outer space accelerators, besides just the data flow. And when reading the papers, it's not immediately obvious what difference exactly is responsible for these smaller output mergers. So just looking at the sparse data structures themselves, our tool can determine that accelerators like outer space will have outputs that are scattered across many more rows than gamma does, while gamma will have outputs that are scattered across many more columns. And the differences can be by up to an order of magnitude. But since the output data format in both accelerators needs to pack elements in the same row together, gamma's output mergers can be much smaller because there's many fewer rows. And that means that we can predict that gamma will have smaller output mergers just by knowing the sparse data structures that it uses, even before we know anything specifically about the data flows in particular. So the math to determine this is actually pretty simple, and we can go into it as well if anybody has questions. But I left those slides out as well to save time. So our DSL can currently express many types of both unstructured and structured sparsity. We have some support for automatic tiling, which we are currently fleshing out further, which can be used to sparsify multi-dimensional blocks within a tensor. The DSL also supports some more sophisticated styles of structured sparsity, such as the so-called fine-grained block sparsity found on NVIDIA's A100 GPUs. Finally, sparse workloads are oftentimes very unevenly distributed, right? So that one PE might have a lot more work scheduled for it, while another PE is sitting idle or underutilized. And that means that sparse accelerators, based on just how their inputs are distributed, may need to be able to shift some of the workload from one overutilized PE to another underutilized PE. So the DSL has ways of expressing this aspect of accelerator design as well. So to illustrate, we can start with an example of a spatial array which operates on sparse data. Initially, we might design the spatial array such that each row in the array operates on a different column of the input data. This fixed mapping, right, can make it easier and cheaper to design the outer memory system which feeds the spatial arrays. However, based on our sparsity distribution, some rows of the spatial array might end up being completely idle on some iterations, while other rows have more work than they can finish in a single time step. So in those cases, we might want to shift some of the future work that is scheduled for one row of our spatial array to another row which is presently idle. Right? This might increase the cost of the outer memory system or the peripheral circuitry, but it can also improve our PE utilization and our performance. So our DSL allows users to specify if they want PEs that are normally responsible for some computations or abstract iteration space to also be responsible for other computations whenever workloads are imbalanced between PEs. So although the exact implications of the load balancing strategy might depend on the data flow or the sparse data format, the user can still specify the load balancing remappings completely independently of the data flow or anything else, just based on how they want work to be distributed across the initial abstract iteration space itself. And based on just how flexible they make the load balancing strategy, we can calculate just how many more I/O ports or crossbar connections need to be instantiated on the actual accelerators so that users can take into account the hardware costs of their load balancing strategies. And finally, after specifying the exact accelerator design in the DSL, our tool converts these into Verilog modules with programming stacks built for them that aim to allow users to easily build end-to-end applications. So right now, Stellar's compiler can generate full Verilog implementations of accelerators designed using its DSL, as well as the 3D visualizations you can see on the right. We are integrated into the Chisel and Chipyard frameworks, if you guys have heard of them, which means our users also have access to host CPUs, DRAM controllers, virtual memory support, all of that full SoC stuff. And when users specify their accelerator in DSL, the compiler also automatically generates a memory map programming interface for them, which lets them build real-world applications. So currently, dense accelerators that are generated using Stellar achieve about the same performance as hand-designed state-of-the-art accelerators from prior work, but they use about 30% more area, which we are currently optimizing down. So the sparse accelerators that are generated are currently less efficient in terms of area and performance, but we are very quickly, polishing and improving the RTL that's being generated. And we expect that within a few months, the sparse accelerators will also be competitive with hand-designed solutions. So that's all, and these are some of the other people who have worked with me. So thank you for listening.